All right, let's jump right in. We're going to tackle something that's all around us, but still feels a little bit like magic: electricity. And I promise you, by the end of this, you'll see it's actually way simpler than you think. No, seriously, have you ever really stopped to wonder how it all works? It's in our phones, our TVs, well, everything. But what's actually going on inside those wires to make your screen light up? It feels super complex, right? But it all boils down to one single, really elegant idea. And here it is, the big secret. It's as simple as water flowing through a pipe. Seriously, that's it. We're going to use that one simple idea, water in a pipe, to unlock the three main pieces of the electricity puzzle. Once you get this, honestly, everything else just clicks into place. Okay, so first things first. For anything to move, you need some kind of push, right? A force to get it all started. Well, in the world of electricity, we call that initial push voltage. So voltage is all about potential energy. Think of it like pressure building up, just waiting to be released. It's not the movement itself, but it's the reason things are about to move. It's kind of like the ready, set before the go. And this is where our water pipe analogy really helps. Just think of voltage as the water pressure inside that pipe. The more pressure, the stronger the potential push. And we measure this electrical pressure in a unit you've definitely heard of before: volts. All right, so we've got our push, but a push isn't very useful if nothing actually moves. So what does voltage times do? What does it create? Well, that's where current comes in. Yeah, if voltage is the potential to move, then current is the actual movement. It's the stream of tiny electric charges, these things called electrons, that are actually flowing through the wire. This flow is what does all the work, lighting up a bulb or charging your phone. And let's go back to our pipe analogy. The current is just like the amount of water, the volume of water flowing past a certain spot. Is it a little trickle or is it a rushing river? We measure that flow rate in amps, or as pretty much everyone calls them, amps. Okay, so in a perfect world, that flow would just zip along with nothing in its way. But we don't live in a perfect world. There's always something pushing back, slowing things down. And that brings us to our third and final piece of the puzzle: resistance. You can just think of resistance as electrical friction. It's basically a material's way of fighting against that flow of current. So a copper wire, it has really low resistance. It lets that current flow super easily. But the plastic wrapped around the wire, that has crazy high resistance. It pretty much stops the flow completely. And to complete our water analogy, resistance is like a narrow part of the pipe, a pinch or a clog. It makes it way harder for the water to squeeze through, which slows down the overall flow. The tighter that squeeze, the higher the resistance, and we measured this opposition in a unit called ohms. So let's recap. We have the push, that's voltage. We have the flow, that's current. And we have the opposition, that's resistance. Now, they might sound like three totally separate things, but the real magic, the secret sauce, is how they're all connected by one simple, beautiful rule. And this is the big question, right? How do these three things, the push, the flow, and the opposition, all relate to each other? If you change one, what happens to the others? Well, it's not random. It's all governed by this incredible piece of physics called Ohm's law. And boom, there it is. V equals I times R. This simple little equation is the key to everything. It tells us that these three things are always in a perfect balance. Voltage, current, and resistance are locked in this constant, predictable dance with each other. This is the bedrock of pretty much all electrical engineering. Let's walk through this with our water pipe, okay? Imagine you increase the push. You crank up the water pressure. That's the voltage. But the pipe's narrow spot, the resistance, stays exactly the same. What has to happen? Well, there's only one possibility. More water has to flow through. The current has to increase to keep everything in balance. It's that simple. And just like that, you get it. You now understand the fundamental rule of electricity: the push, the flow, the opposition, and the simple law that ties them all together. Seriously, every single circuit, from the one in a tiny flashlight to the one in a massive supercomputer, plays by this exact same rule. So I'll leave you with this little puzzle to think about. A dimmer switch on a wall makes a light bulb get, well, dimmer. It does that by reducing the current going to the bulb. Now that you know Ohm's law, how do you think that little switch uses resistance to pull that off? Pretty cool, right? Thanks for tuning in.